Right. All right. Welcome back to the lectures on the double operatic theory of systems. Today, we're going to continue what we were doing last time and describe how the categories of Moore machines of various sorts, which as we've seen, include not just the traditional Moore machines or things like Markov decision processes, but also systems of ODEs. How they are organized into a loose right module over some appropriate double category of lenses. So let's just recall, recall, if we have a fibration, P to B, E, P, of categories, right, it's double category of lenses, is all right, my double category is blackboard bold. Lens, I'll just usually put lens E instead of lens pi, but it really is lens pi. Defined equal to be the spans in the adequate triple E vertical Cartesian. So what are those? Again, so we have a map in an object in E is something like A minus that maps to something via pi in A plus. So we usually write it as this pair, but that's just sort of binding the name A plus to be pi of A minus, if you want. And if I have two of these, it looks like this. And then in the middle, right, now I'm going to take a vertical map. So I have to, on the left, and a Cartesian map on the right. So down here, I have something here, which I will call F. And then up here, I pull back this thing over here to get a Cartesian map on the right. And then I take a map going the other way, which is vertical on the left. And this I call F sharp. So that is an example of a span. This is an example, if we will, of a span. It goes from A minus over A plus, and we write it like left, right arrows, or maybe I'll write it using in the double category notation. We would write it as an arrow that's broken in the middle. So this is called a loose arrow in our double category. And it goes to this pair over here. We see it's a pair F sharp, but it's actually a span, right? So now suppose we have another one of these. Right here, but now we name these differently. So I'll name this C minus, C plus, C plus, D minus, D plus. This will be G, let's say. This will be G star, D minus, and this is G sharp to C minus. Again, another one, right? A map between these. So this down here would be something like C minus, C plus, D C minus, right? So now in a double category, we have two kinds of maps. We have maps that are loose, which are going to be these spans, and maps that we call tight, which go in this vertical direction. I'll usually draw them. And then we have squares, which are maps that sort of live in these squares between these things. So this is a double category. And so we'll see that the kinds of maps we have here are pairs of these maps like this. That beeping is going to happen the whole time. So apologies. Um, and then the square in the middle is going to be one that goes like this then. So we have this diagram on the right is the picture way to say this diagram here on the left. And then note that I will call this one, say, J and J flat, and this one here, K and K flat. All right. And then this in the middle, as you can see, is actually, that thing in the middle is actually determined largely by the data here, because as you can see, the thing in the middle, which I'll highlight, the thing in the middle, it has to make this diagram commute, which means in particular, it has to make this square commute. But since these are both identities, or in general isomorphisms, I'm not going to be too careful about that. This middle thing must be K. Okay. And once we have that, we're asking that Fj equals Gk. So that's a property. It's not necessarily true, but if that's true, then we get an induced map on the pullbacks like this. And that's by sort of the functoriality of taking these inverse images or pullbacks, which uses the property of vibration.
Can I just ask a notation question? So
yeah,
has K flat at some point been used to describe the map from A minus to the pullback of C minus rather than?
Yes, technically it's being used. I mean, it's technically being used to describe the map from A minus to C minus in E, and K is its image under pi. But of course, that's equivalent to giving a pair of a map K below and then a map into the pullback of K. I'm not going to be too serious about keeping track of these distinctions all the time. The point is that they're equivalent and the same data is involved. So I'm not going to be that careful because it's often easier to understand in the theoretical sense when you use the span picture just in E, but it's often easier to write down specific examples if you use the other one. And so I'll like the freedom to just jump between them. Okay. So the point I'm sort of making there is that asking that there be a cell in here is a property. It's not an extra structure. It's not like we have to give an extra morphism there. In fact, we just have to check that certain facts are true about the already existing morphisms, which is to say specifically that this bottom square commutes. And then for the induced map up here, induced by K, noting that this bottom square commutes, that this top square commutes. So there's two facts to check there. So, right. So that's the double category, right? And it being a double category means it has two kinds of composition. So I'll just do. So I'll do a refresher on double categories. So a double category consists of objects. Let's just say A, B, C. So-called tight maps, which I'll write with a solid arrow. B. So-called loose maps, which I'll write with a broken arrow. And then squares or cells. Sometimes I'll say cells. Cell is a generic term for higher kind of morphism in a higher kind of category. So, so if we have four objects, we have two loose morphisms like this, L naught, L1. We have two tight morphisms like this, F naught, F1, then we also could have a morphism F here that lives between them. And sometimes I'll just write this as F goes from L0 to L1, and we'll just remember that for that to be the case, it also has to come with a tight boundary. So the rules are, so the axioms are that one, this is like, it's a category vertically with these squares. So what that means is if I have a square like this and a square like this, I get a square like this. Well, so F0, F1, G0, G1. I get a square like this. L0, L1, L2, L0, L2. Where this, I would write F over G. That's not a fraction. That's just a nice notation that kind of looks like the way that we're actually composing these. And over here, this one is G0 after F0, and this one here is G1 after F1. So the tights form a category like this. And then for it to be a double category, too, the looses form a category. So let me say what that is. So we have this other kind of composition here. So if I have L0, L1, L2, L3, and this is F0, F1, this is F, and this is G, G1, right? Then from there, I can form the composite here, which I'll call, and it has the appropriate boundary. So here, I'll call this L0, and then we usually use this little like tensor product looking notation. L2 dot L3. And the maps here are, I would call this F bar G. And then both of these are roughly speaking a category. I'll come back to that. I've left a very suspicious space here before the word category. And then 3, we have the so-called interchange. And this says that if I'd had three squares, F0, or well, I don't know. I'll put the thing up here. F0, F1, then F2, F3 is equal to F0, F2, or F1, F3. So this is as you can see, the lines break either way. So what does that mean in terms of these pictures? Well, it means that if I have an arrangement of 4 squares like this, crap. F2, F1, F3, right? If I have an arrangement of 4 squares, there's a unique way to understand what it means to write this composite of 4 squares like that. And so either I take the 2 vertical stacks, compose them, and then compose the result horizontally, or I take the 2 horizontal stacks, compose them, and then compose the result vertically. And those are the 2 sides of this equation. So saying that that's the same is just saying that there's no difference. Now, the thing is, this would be great if this is what's known as a strict double category, what I've just told you about. But this is, in fact, generally only a pseudo category. And the reason is that very often in a double category, its objects will be mathematical objects, and its type maps will be some kind of map between those mathematical objects. But its loose maps will also be like mathematical objects themselves. And the squares will be like maps between the loose maps. And the composition of loose maps will be a composition of the mathematical objects So it's going to build a new kind of mathematical structure out of the two mathematical structures. And the issue is that any kind of construction you perform on mathematical structures is, generally speaking, only really well defined up to isomorphism, because you're going to have to make some specific labeling choices at some point in that construction. Those labels are arbitrary and could have been chosen differently. What that means for the definition of a double category is that, in fact, so this is plus associativity, associative, and unital, like a category, right? But here it's only associative plus unital up to isomorphism plus laws for those isomorphisms. So if I really don't want to spend too much time dealing with the particularities of coherence, although I will spend a lot of time on the techniques used to avoid dealing with those coherence. So maybe it's good to see what it looks like once. So what happens if we have three loose arrows? The same thing is going to hold for squares, by the way. So I'm just going to do it for the loose arrows, but like everything will have to happen with squares composing in the loose direction. But so suppose I have three loose arrows like this. Remember that these could be something like spans. So maybe I should say a little more about when I say that the objects are usually like mathematical objects and the types are like maps. Consider the double category of spans, say spans of sets. Then the objects are sets, and the type maps are maps of sets. But a span is also a set with extra structure, the maps to the two legs. And a map between spans is then a map between those. When we compose spans, we compose them by taking pullback. And that pullback is associative, but it's only associative up to a coherent isomorphism. So I'm going to walk through that. Yeah. So there's two things we could do here. If we have three of these in a row. So one is that we could form these two, which is L naught dot L1, L2. And then one is that we could form these two, which is L naught L1 dot L2. And then we can combine them both into being one thing. So if I take this side, right, I would get L naught dot L1 dot L2. And if I did this side, I would take L naught dot L1 dot L2. And if to say that composition was associative would be to say that these are equal. But I'm not going to say that they're equal. I'm going to say that they are isomorphic. And that isomorphic will be called alpha. Really, it's alpha labeled by, it's alpha L naught L1 L2. Like alpha is a function of these three things. This is called alpha. And alpha is called the associator. It is an actual thing that you can do which reassociates. Similarly, we have a uniter. So the uniter would, we have a loose identity and a uniter on the left and the right for that, but I'll just do associators now. So now that's all well and good. That would be enough to know it was associative if it was an equality. But now that we actually have something there, there's something else we can do, right? So let me see if I can do this quite right. I'll do it. Suppose we have four of them, right? So now I can take the first two, I could take the middle two, and I could take the end two. I'm definitely not going to arrange this on the first try in the right way that looks good. Although I do like doing it more systematically like this than just starting from the binary one. Okay. So right, and then this is not quite right. I probably should have started by threes. Can you pause it for a second? Okay, so first let me actually explain what it actually means to have such a thing, right? We have two things. If this went from A and this is D, right? This is A and this is D. Here would be L naught dot L1 dot L2. But then we also have A and D here. And here we have L naught dot L1 dot L2. And now remember that in the tight direction, which we're drawing vertically here, they have a there's actually a category there. So in particular, I do have identities. So I can put identities here. And what we're asking for is that there be a square called alpha, which lives here, and that square is invertible in the tight direction. So this is a tight isomorphism. So now, if we go out to 4, we can see that something fun happens. Okay, so suppose I start completely associated in this direction. Now I can take one step of the associator here and reassociate into the in the first component. Right? So this is going to be alpha dot L3. Okay. Then what I can do is I can take this expression here and I can reassociate it to get L naught dot L1 dot L2 dot L3. And what is that? Well, that is an associator, but it's an associator of L1, L naught, L1 dot L2, and L3. Right? And then I can do the associator L naught dot associator to get L naught dot L1 dot L2 dot L3. Okay. But on the other hand, I could have done a different thing here. I could have, instead of reassociating that inner one, I could have reassociated it straight away to something like this, L naught dot L1 dot L2 dot L3. Right? So that's the, if I name all these associators, it's probably better, but this is the L naught, maybe I'll just use the, I'll stop drawing L's. This is the 0, 1, 2 associator. And then we carry 3 along for the ride. This is the 0, 1, 2, 3 associator, where we take L1 dot L2 altogether. This is the 1, 2, 3 associator, working on L1, L2, and L3. This one here is the 0, 1, 2, 3 associator. So we keep 0 L naught dot L1 as a single object, and then we reassociate there. And then we can go straight from here to here by flipping there. So this is the associator for 0, 1, 2, 3. And this is supposed to commute, which is called MacLane's pentagon. And so this is a little Baroque. I started drawing something that would have given a sort of more natural explanation for why we care about this pentagon, but I couldn't really do it from the top of my head, and it's also not something I want to spend too much of our time on, even though this is a very cool and deep area of category theory. It also is somehow entirely trivial, except that it's also entirely not. There's a deep relationship between these shapes and cohomology. But but we're not going to do that. Let me show you how this happens in practice in pullbacks. So for span in some adequate triple here, so this could be, for example, in lenses. It could be in spans. It could be in cospans, right? They're all going to sort of work the same, but let's just say we're in spans, right? I'm going to forget about the L's and R's here. All that means is that all the left legs are in L and all the right legs are in R. So now let's see what this situation L naught, L1, L2 is. What does that mean? Well, let me give some names to this. So we have objects A, B, C, and D, and then we have three spans, L naught, L1, L2, right? So now let's see what let's take the composite that would form. I'm going to do two composites over here. Boom. So on this side, let me describe L naught dot L1 dot L2, and on this side, let me do L naught dot L1 dot L2, and we'll see what the associator has to be. So in here, we first compose L naught and L1. So what do? Well, we take this pullback here. And then we compose the resulting span with L2. So here we get L naught kind of a nice looking diagram. And on here, we do it the other way around. We take L1 and we pull it back over C, L2. And then over here, we also pull it back, the result over C, over L naught, excuse me. Okay. So these will be the same. And there's a abstract argument, but there's also a concrete argument. And I'm going to go through the concrete argument first. So let's suppose that these are all sets. So they have elements, and I can just talk about the actual element-wise construction of these pullbacks, right? Then we have that this is equal to the set up top of things like this. It's things x naught, x1, x2 in L naught times L1 quantity times L2 such that, well, if that the I would have to name these such that, but I'll just call it restriction. X naught restricted to B is equal to X1 restricted to B, and X1 restricted to C is equal to X2 restricted to C. So that's the pullback at the top on the left, right? Note the arrangement in here. The arrangement of the pairings of its elements matches the arrangement of the pairing of the actual product we took. In other words, its elements are pairs, but the first element in that pair is a pair. Right? And over here, this one is equal to the other way that we could write this. Again, it's a pairs, but now the first element is just an element of L naught. The second element is a pair. But it's the same equations. So the isomorphism alpha between these is obvious. Alpha of x naught, x1, x2 is going to equal x naught, x1, x2. That's sort of obviously an isomorphism because the inverse just takes the parentheses and puts them in the other order. So all that the pentagon axiom says up there is that if I take something arranged in that way and I shuffle the parentheses over until they're all arranged in the other way, it doesn't matter the order in which I shuffle all the parentheses over. The resulting thing is the same. So as you can see, it's like very somehow it seems very trivial, but this is yeah. So the sort of abstract way that we can see that this works is I'm going to put in the middle. What if we took both of these composites at the same time, right? And then composed the middle one. So by the way, up here, right, this is things of the form x naught, x1, x1, x2, x1 prime, x2, such that x naught restricted to b equals x, sorry, x1 restricted to b, what, x, sorry. Such that x naught restricted to b equals x1 restricted to b, x1 prime restricted to c is equal to x2 restricted to c, and x1 equals x1 prime. Boy, that's a mouthful, but that's really what we're saying up there. So these elements are two pairs. We took both sets of pairs there, and then we took a pair of them, and then, but we added an extra equation, which is that middle box equation. Well, you can see that we sort of factored either diagram into it, and we have this middle one. And that middle one sort of is, no matter which way we went, we could always go into that middle one. And so one way to say that we resolve this issue is to note that we actually can always form these n-ary composites, and then we can compare every sequence of binary composites to that n-ary one. So this is actually, it's a deep and complex field of subfield of category theory looking at these coherences. They get more and more complicated the more higher dimensional your category stuff is. We'll never really need to go above here, except that we're about to look at symmetric monodal double categories, which sort of do this again, but now on the objects. And so my point of view is that as much as possible, the entire theory should be set up to avoid having to work with these problems on a hand, like by hand. They do show up in implementations of this, having to do with, say, like, you know, there's a difference in a file structure between, you know, 3 files, but 2 of them are in one folder and the other one's just in the top folder, and vice versa, right? These are 2 different file structures here. So when you're actually representing models in practice, they do have the exact same issues. This is not like some quirky issue of mathematics. This is just a practical issue of naming things. Nevertheless, on the theoretical level, we would like to avoid having to spend all of our time shuffling around parentheses. Yeah. So that's all I'm going to say about the pseudo categoryness for now. So spans are an example of these pseudo category things, but as I sort of suggested here, the result of this, the pseudoness is really only about rearranging these parentheses. So it's not that essential. It just doesn't matter that much. If you have these 2 file systems over here, they have the same files. That's the point. Right? But of course, if you were trying to access those files, you would need to know which one you were in. Okay. So It does matter, but it is kind of boring. Okay. So that as we've seen, this problem also afflicts these lens situations. However, lenses can be what we call strictified. You could present them in a way that you actually get a category for the looses. And again, I'm not going to really belabor this point after this. Okay, so that's our refresher on double categories. Now, so we have our double category of lenses. Maybe I'll scroll back up to our double category of lenses. Here's our double category of lenses, right? So now note what this means, that this is a double category, and it's a double category because it's a double category of spans, right, of a special sort. What this means is that we can also put together these squares like this. We could compose them horizontally. We could also compose them vertically. And then we could do both, and it wouldn't matter which order we did them. Right? So these are important things. If I started writing out these in full, you see that the page would get very, very cluttered. But the point is that once we know we're in a double category, we know we can just work with these squares rather cleanly. We can paste them into square shapes or rectangular shapes, however we like. Okay. So knowing that is actually quite nice. So uh, so results about behavior from being the double category of lenses. So we know that lens E is a double category, and we also know that a system is a lens. Like that. And I cannot remember if we already covered whether or not solutions to systems or behaviors of systems are maps. But let's take this to be E to be manifolds. So vector bundles of manifolds, or not, yeah, vector bundles of manifolds. So that the thing on top is a vector bundle. Okay. Then we have a solution. This is a system. Now it's of ODEs in this case. Right here we have our E, we have our U. Our U gives us a differential equation. This is ds dt equals USI. And of course we have the expose as well. A solution is a square. TR, R, R. Well, this is the point. And here we have id, and we have 1. So 1, i.e. dt dt equals 1. And a solution is just a map like this, TSS. Oh, well, first we pick our parameters. So we pick our outputs here, O, and we pick our parameters, P. Recall that this is P is a section of the bundle. So in other words, this is a square. R equal R over here. I to O. We have our O, and we have our P. Okay. That's what that looks like. And then over here, we have phi, or maybe I'll just call it S. We have S, TS, right? Maybe I'll draw the whole diagram over here. So these two things. Now let me put my system over here. Or, well, that is an actual bundle, so. Here's my system. Then here's my real system. My clock system. Oops. This is R. This here is 1. So now we have these maps OP. We map down from here to here. That is my little s. It's a function of time. This here is TS, which is the derivative of the function s, right? And now we ask that this be a morphism of these spans. So again, what that means is this bottom square commutes, i.e. E after S equals O, right? In other words, E of S of T equals O of T for all T and R, right? In other words, we've picked O as our expected observation for the system. And we're giving solutions that act as that observation. Okay? And then we have the top square, right? So what does that say? That says that TS after 1 is equal to U after E star P, right? Okay, that's just what the top, this is. So this equation is this square. This equation is this square. So what does that mean? Well, remember that the derivative, this here is a derivative, right? This here is going to be ds dt as a function of time. And on the other hand, we have u of s, and then we have e upper star p, so that's p of t. Oh, and I need to put s is itself a function of time here. And that's what we've done here. So that says that we've solved the differential equation. So this is a solution of the differential equation UE. It's mapped like that. Well, now we can know some cool things, right? We know already something very fun from being in a double category, right? So corollaries. We know that any morphism of systems preserves trajectories. This is maybe not too surprising. It's essentially what a morphism of systems mean. Trajectories. Right? So what's a morphism of systems? Well, suppose I have I prime, O prime. I have T S prime, S prime here. And I have a map here on the interfaces. And I have a map here phi, T phi. And this constitutes a morphism of systems, means it forms a square like this. Well, we're in a double category, so we have tight composition. So the outer square, the composite here and here, is a morphism of systems from the clock, which is a trajectory. So we get that. Okay, so that's kind of fun, but perhaps not that interesting. What's more interesting is that we get a result about coupling. So remember that a wiring diagram, a coupling, took the form of a lens like this. Now, in general, we might have multiple systems on the left-hand side, and we'll come back to that in a moment. But for now, imagine that we have, for example, this wiring diagram here that just feeds back some things into S. So suppose that this was W sharp. We can walk through this example in particular. In fact, it would probably be a good idea. So now, if I want to understand when does the trajectory of my system, when is it a trajectory also of the coupled system? Well, because I'm in a double category, to me, it's quite clear. If I put the identity up here, well, I need to choose a new I need to choose some kind of new thing up here because it's not clear that the original choices still work after all. I have new sets there. And so now excuse me, if the if I have a square like this, then I get an outer square. And what is that outer square? Well, this is still one id, at least up to isomorphism. I'm not going to fuss with that. And this one here is the composite system, right? The one that's coupled. And for us, it's the one that has the feedback. And so now we've reduced the question of does this coupling law preserve our trajectories to can we give something of this form, right? In other words, we can see the existence of this, right, which is a predicate, as relating the coupling law, the parameters we chose here, and the new parameters here. You might, in general, try and ask, when can we complete shapes of this form to shapes of this form? Right? Okay. So let's actually see what that literally says, because it says something very, very explicit for actual coupling laws. Like it says a bunch of obvious equations you can obviously check. It's not saying things that are miraculous. It's organizing a bunch of obvious facts that would be hard to notice if you didn't try to organize them. Okay? So let's actually write out this particular example, right? On the side here. So I'm going to assume all of those wires carry real numbers. So again, remember that this gets turned into a wiring diagram, right? Where the inputs are going to have there are two inputs, there are two outputs and there are two inputs. Right? And we're going to go to an interface with one output and one input. Right? And remember that we actually know exactly how to turn these pictures into these lenses in a very rigorous way. Right? But it's also exactly what you would get if you just looked at it and thought about it. So let me just look at it and think about it instead of going from the free one. But that's the systematic way to do it. Gives you the same answer. So W, this is W sharp. So W has to take two things here, X and Y, and it gives me one thing. It gives me clearly the second thing if I order them from the top to bottom on the picture. W sharp, right? It has to take X and Y and an input Z, and it has to give me two things, right? Which are the two inputs. So as you can see, I'm taking X and I'm putting it in the first component, and I'm taking Z and I'm putting it in the second. So if I think of this as X, Y, and Z, becomes clear how those shuffle in. Okay. Okay, so that's that. Now suppose I have a system. S, well, squared, R squared. Right? Okay, so now let me ask the question of what does it mean to have sorry, before I write this system down. Bye-bye. Let me ask, what does it mean to have a square of this form? Well, here we have two functions, O and P. Both of those are pairs of pairs, right? They're time-valued functions into pairs. So I'll write it like this. Down here, I will write it as x, y, and here I'll call it x prime, z, for reasons that are going to become obvious. And then here I have three other functions. So I'm going to call it x bar, excuse me. I'm going to be really cheeky. This is going to be called y bar. This is going to be called z bar. We don't know anything about these. Except that we're now going to get a bunch of equations by asking that this be a square. And what are those equations? Let's write out the actual span stuff, because that's what this means. Remember, such a square actually refers to a map of spans. So again, here I have R equals R. I have that equals R, and that equals R, which equals R. And then that equals R, which equals R, which equals R. That's my identity on R equals R. That's what the top line is. Then all the way down here, I have R2, right, times R2 over R2. Because remember, my notation, I'm a little bit fiddly with this, but when I say that, when I have a Cartesian diagram here where I'm like have just numbers of things up here and they're not varying with the bundle, it always means the simple vibration. And over here, I have R times R for R. And then here I have R squared, and this is W, that equals, and then I take W star, well, I can compute that one, because that's a product. It's pretty easy to show that this is just R squared times R. Here, it's a pullback, and then my map here is my W sharp. Well, that's actually only the second component of my map there. It's actually also the projection. Okay, and then of course I've drawn this in I'll just give a new color here and try to, maybe I really need to move this out here. Oh boy. Okay, so now I'll give a new color. And we'll look at what, so here you can see this coming in here, that's x, y. Two real valued functions landing in R2. Okay, so a single real valued function landing in R2, therefore two real valued functions. Up here, well, up there, it's actually, well, first in the first component is xy because that square commutes. And then in the second component, we have two more functions, which I've called x prime z. These are just names for now. They've, of course, been judiciously chosen. Over here, I have a function, which is y bar. And over here, I have another function. Again, it's a pair, but the first one has to be y bar, and the second one is free, called t bar. And then I've asked that, in fact, in the middle, there are two functions like this, which, as we described before, because this left square commutes, this has to be x, y. And now we get our first equation. This bottom square commutes. What does that mean? Well, that bottom square commuting means that w of x, y is equal to y bar. But we already know, right, that w x, y equals y by definition. So this means, i.e., y is equal to y bar. Next, we take this map here. What is that map that's induced up there? Well, it must be x, y, comma, z bar. It's just what it has to be because it's induced by the pullback. And so now we get our second equation. Oh my God. Which is this one. And that second equation, we would write this guy over. Whoop. The second equation, as you can see, says that W sharp, I'm going to just do it in the second component, of, as you can see, x, y, z bar is equal to, and I'm just looking at the second component, x prime, z. But again, we already know what W sharp is. We defined it up there. So i.e., we have that x comma z is equal to x comma z bar, excuse me, is equal to x prime comma z, i.e., x equals x prime and z bar equals z. So what the theorem really says, right, is that if you had so now the theorem, just to remind you, says that if we have any trajectory of this system and we compose it with any square like this, we get a trajectory of the same system that had been coupled according to that law. So what this says is that if the parameters you chose here were compatible with this coupling, in the sense that when you chose parameters for the inner system, remember, you were saying, well, you chose two things, right? You were saying, here's the output behavior I expect on these wires, and here's the input parameters you're allowed to plug into the system, right? Now, what this theorem says is that if you take on the outer system, you take this parameter here to be whatever you set this one to be, you expect the same thing. And if you take these two parameters and you make sure that this one was equal to this, whatever you set this one to be, and you make sure that this one gets sent into that one, exactly as the wiring diagram says, under those circumstances, you get a trajectory for the composite, which again is, strictly speaking, sort of obvious, right? It's just how it must work. But the nice thing about this is that it comes from this abstract algebra, that we've deduced this from this abstract algebra. So we'll be able to prove general theorems about this. It's true whether or not these are ODEs. It's true if these are Markov decision processes that are of multiple agents communicating stochastically. It's true in situations that you have a bunch of more machines and you want to know how they couple up together and they want to hook up together. All the examples we've seen so far, and we'll also see that the same points of view give us theorems for labeled transition systems or Petri nets and various other kinds of things on the road. It's in fact very general to know that your behaviors are representable in a double category. How are we doing on time?
We could stop that now.
I think this is good, man. Any questions? Yeah.
Yeah, I have a question. So just interpreting this, it's saying that like we've got a solution for the system, the IO system, and then we've got this map from I prime O prime. And we're looking at when we can extend that square. And I guess this is saying that there's a unique way to extend that square. We must have Z bar as Z, Y bar as Y. But it's also saying that like only certain solutions to the left admit.
Only some of them actually admit extensions. That's right.
Okay.
So I don't know of a general way to say when you can extend. But I do know that if you do have the extension, you get the results, and that's the way that I will formulate this. It will be we will eventually package all of these. So we had the corollary, we had the first one, which was about tight composition. And we have this one, which is about loose composition. And of course, they interact because there's the interchange law. We're going to package all of that into one big functor that takes systems and gives you sets of their solutions indexed over the choices of the boundary behavior. And then we're going to take wiring diagrams and give spans over the behaviors of the two interfaces. And the spans will be the relation that two behaviors are related by the existence of such a square. So it will be the compatibility relation. So we're going to give a sort of functorial way of turning every wiring diagram into the compatibility relation between the choices of interface behavior.